Hi everyone, and welcome to this tutorial. Today, we'll take an in-depth look at gradients, one of the most important concepts in machine learning and optimization. If you've ever wondered how models like neural networks or linear regression learn from data, the secret lies in gradients. In this tutorial, we'll break down what gradients are, how they work, and how to compute them, both mathematically and in Python. Let's dive right in. Let's start by understanding what gradients are. Imagine you're on a mountain with a scalar value, like height, assigned to each point. At any location, you want to know which direction will lead you uphill the fastest. This direction is given by the gradient. It tells you two things: the direction of the steepest ascent and how steep that ascent is. In simple terms, gradients are a generalization of derivatives for functions with multiple variables. If the function depends on two variables, x and y, the gradient is a vector. The first component represents how the function changes with respect to x, and the second component represents how the function changes with respect to y. These are called partial derivatives. Let's connect this concept to machine learning. In machine learning, we often deal with a loss function. The loss function tells us how far off our model's predictions are from the actual values. The goal is to minimize this loss function by adjusting the model's parameters. Gradients help us find the direction in which the loss increases the most, so we can move in the opposite direction to reduce the loss. This process is known as gradient descent. Let's consider an example to make this concrete. Suppose we have a simple scalar function, x squared plus y squared. This represents a bowl-shaped surface. The gradient of this function is 2 times x and 2 times y. At any point, the gradient points directly away from the center of the bowl, which is the lowest point. In gradient descent, we move in the opposite direction of the gradient to find this minimum. Let's compute the gradient of this function at the point 1, 2. Substituting x equals 1 and y equals 2, the gradient becomes 2 times 1 and 2 times 2, which simplifies to 2 and 4. This means that at this point, the steepest ascent would involve increasing x by 2 units and y by 4 units. In gradient descent, however, we move in the opposite direction, reducing x and y by these amounts. Let's begin by defining a scalar function in Python. First, we import the necessary libraries, numpy for numerical computations, sympy for symbolic mathematics, and matplotlib for visualization. Next, we define two symbolic variables, x and y, using sympy's symbols function. These variables will represent the inputs to our scalar function. We then define the scalar function as x squared plus y squared. This function represents a paraboloid surface in three-dimensional space. Finally, we print the scalar function to verify its definition. The output will display the formula, confirming that it has been set up correctly for further computation. Now let's compute the gradient of the scalar function symbolically. Using sympy, we calculate the partial derivatives of the function with respect to each variable, x and y. This is done using a list comprehension that applies sympy's diff function to each variable. The result is a symbolic representation of the gradient, which we print to verify. Next, we evaluate the gradient at a specific point, in this case, x equals 1 and y equals 2. To do this, we substitute the values of x and y into the symbolic gradient using sympy's eval function. The evaluated gradient provides the numeric values of the gradient at this point, which we print for confirmation. This step demonstrates how the gradient changes at a specific location on the scalar function surface. Finally, let's visualize the gradient field of the scalar function. First, we use numpy to create a grid of points in the x and y directions. This grid will span from -2 to +2, with 20 evenly spaced points in each direction. Next, we calculate the gradient components for the entire grid. The partial derivative with respect to x is 2 times x, and the partial derivative with respect to y is 2 times y. These values define the direction and magnitude of the gradient at each point on the grid. Using matplotlib, we create a quiver plot to represent the gradient field. Each arrow in the plot shows the direction and strength of the gradient at that location. Arrows near the center are shorter, indicating smaller gradients, while arrows farther from the center are longer, representing steeper gradients. This visualization helps us intuitively understand how the gradient behaves across the function surface. If you found this video helpful, please like, share, and subscribe to support the channel and stay updated with more informative and engaging content. Thank you so much for watching, and we'll see you in the next video.